Now that we know how data is organized, let's look at what actually happens inside. Physical RAM and memory addresses. Physical memory in a computer is a vast linear array of bytes, each unequally identified by hexadecimal memory address. Data structures are simply architectural blueprints for mapping logical data onto this raw, unformatted byte grid. Every variable, node, and element in a data structure occupies one or more contiguous or non-contiguous memory locations that relies strictly on absolute memory addresses to fetch, modify, or store this digital information.
When a program accesses an array element, it calculates the target address using base address arithmetic by multiplying the index by the data type size and adding it to the base. The computer jumps instantly to the exact byte. References and pointers store memory addresses rather than actual data values. This level of indirection allows complex structures like linked lists to scatter data across random physical RAM locations while maintaining logical order.
Visualizing RAM as a massive grid reveals how static structures like arrays demand contiguous blocks. If a contiguous block is unavailable, large array allocation fails, even if total free memory is ample.
Gearreferencing is the runtime process of following a pointer's stored address to read or write the underlying value. VICTO pauses momentarily to perform an extra memory fetch cycle during every traversal. Non-contiguous structures like trees and graphs rely entirely on internode references. Managing these references requires meticulous tracking to prevent infinite loops or orphaned memory branches during updates.
Compilers translate high-level data structures into low-level memory layouts by determining precise byte offsets. For every struct, member heading bytes are often inserted between fields to satisfy hardware alignment rules.
Contiguous data structures like arrays excel in cache locality, because fetching one element automatically loads adjacent elements into fast to cache. Scattered pointer structures cause frequent cache misses, degrading execution speed. In high-frequency trading and game engines, understanding memory addresses prevents costly latency spikes. Engineers carefully pack data structures to fit precisely within cache lanes, minimizing RAM round trips. Mismanaged references lead to severe bugs like memory leaks and dangling pointers. When a data structure node is deleted without freeing its memory address, the RAM remains locked out until program termination. Hardware processors prefer reading memory addresses that are multiples of 4 or 8 bytes. Data structures use padding to align member fields, trading a tiny amount of storage space for massive speed gains. Choosing between arrays and linked lists is fundamentally a hardware compromise between memory address continuity and dynamic insertion flexibility. Each choice dictates how the compute interacts with physical RAM.
Heap allocation routings manage memory blocks by maintaining internal free lists of address ranges. When a data structure grows, the allocator searches these free lists to assign valid non-overlapping memory addresses.
Manage runtime environments utilize garbage collectors to automatically scan memory references. By tracking active pointer graphs, runtime systems reclaim orphaned memory addresses without manual developer intervention. In languages like CAN, pointer arithmetic allows direct manipulation of memory addresses. Incrementing a pointer automatically shifts the target address forward by the exact byte size of the data type.
Frequent allocations and deallocations fracture free RAM into tiny isolated pockets, causing external fragmentation. Advanced data structures employ custom memory pools to bypass general allocator overhead entirely.
Modern operating systems use virtual memory and translation look-aside buffers to map logical data structure addresses to physical RAM frames. This abstraction ensures programs operate in secure, isolated memory spaces.
Mastering how data structures utilize memory addresses and references transforms code from functional to lightning fast. Every pointer offset and catch line optimize brings tangible performance gains to software systems.